Thank you. Yeah. Hi, everyone. Yeah, that's great to be here. It's my second speech, and it's awesome to come back to this same room. So I had my speech at this same room. So let's start a bit of intro on top of that. So I'm Mark. I'm currently working at Meta in marketing. For the last 6 years, you can see where I've been working in and where I've been living in. And for these 6 years, my passion still is in causal inference and experimentation. And sometimes I'm feeling like this, that like all this hype, like LM, GenAI, RAG, and other stuff. And sometimes we're forgetting about like foundations, experimentation, and A/B testing. And that's lovely that we have an opportunity to discuss it here. That's cool. So, as I guess most of us have guessed, it's going to be about experimentation, and to be specific, about how we can use regressions in it and how it can improve our pipeline. So let's just start with some basics. So A/B testing, what it is. So it's a gold standard approach how to find causality. So how it works, we just split the users usually into groups. So control and test. So control, we have still this great blue button. And for test, we have this green one. And the idea is we want to measure our parametric. In this case, it's conversion rate. So it's like 10% and 15%. So we got like the difference of 5. And the question right now that comes is that like just do it to the random, or it's really because of the change of the color that I have some doubts of, but anyway. And there are many approaches how we can detect if this difference is caused by our change, or in other statistical terms, statistically significant or not. And the list is huge, right? So it's ranges from bootstrapping and bucketization to like Welsh and Mann-Whitney and other things. I don't know even 50% of them, I think. Not here, but overall. But what's the most popular method and that we use all the time, everywhere, at every company, every person? So it's like t-test. So I'm not going to dive into like some technical things about t-distribution and things. I will just explain how it works in reality. So for t-test, we want to calculate t-statistics. So we just going to find the laser. Yeah, here. So t-statistics, so we're measuring this observed difference. And in our case, it's like 5%. And we divide it by the random variation in this both group. And also for relating to sample size. So the idea is if this t-statistics is big enough, we can say that it's not due to random, it's really because our change caused it. To simplify things, we also introduce p-value. So p-value is just probability of getting this t-statistics value, or more extreme, under the assumption that there is no impact at all. Yeah. So we just assume that there is no impact, and we're measuring this difference over some variance, and then we define if it's like random or not. But the question, the next question is why t-test is so widely used, and it's like used everywhere. So there are two, I would say, main points here. So the first one, it's easy, right? So it's easy to compute, it's easy to understand. And even to compute, you don't need like Python or some other things. All you need is like SQL, right? So, and in many companies and for many projects, we don't use like Python or something. We just use SQL to calculate it because it works better for really big data. And second one, also pretty important, that main assumptions are held when we're using t-test. So there are three main assumptions: independence, normality, and equivariances. So independence So it's held on because of, I hope, a good measurement design and randomization. Normality. So some people think that we should have normal distribution of data to use t-test, but that's not how it works. We should have normal distribution of means of this data. And it works for enough sample size, mostly everywhere, due to central limit theorem. I'm not going to prove it here, but yeah, you can check it out. And equal variances. So in most practical cases, we just don't assume that variance can change. So we have similar size groups, we have conversion metric, and we just don't expect that variance can be different. So, but if t-test is so great, why we're looking for some other options? There are two things of it. One is power. So power is our probability to detect the stat-sig difference, if there is one in reality. So we're always looking for things, how to boost it. Yeah, because ideally we want to have 100% chance to detect it, if it's going to be possible, but obviously it's not. So our common choice is 80%, but we are looking for some ways how to improve it. So what influence power? There are three things. So it's sample size, it's the impact that we are looking for to detect, and it's variance. So sample size, it's not the best choice because if we increase sample size, so the duration is also going to be increased, and we want to run more experiments and in less time. So that's not what we're looking for. So the impact that we're looking for, or MDE, minimum detectable effect, is also we don't want to increase because most of our experiments are focusing on really tiny percentage, and if you're looking for the change of 20, 40%, you don't need to run an experiment. And variance, that's what we're looking for to change. And the second one, unknown variance. So when we're using t-test, all the variance of the metric, of our target metric, we define as noise. So, so we define as noise, and we don't explain it, right? So it's just unknown variance that we can somehow to work with, and eventually we can detect more powerful changes, and we explain better with some models if we know where the variance is coming from. So the solution to fix most of these things is regression. And to dive into this, we should start with, t-test, unfortunately. Again, t-test is just a regression, and I'm going to show you why here. So this formula, I believe most of us are familiar with. So it's just linear connection between our y outcome and x covariates with some random noise epsilon. So this table just shows how it's going to look like when we're running an experiment. So we have user ID, it's not very important. We have x. X is either 0, 1 here, so it's either control or treatment group, and y, it's our target metric. For example, here it can be average duration of the sessions. Let's talk about what exactly means beta 0 and beta 1, these weights. So beta 0, it equals to our outcome only when x equals to 0. It equals to 0 only if it's control group, right? So it means that beta 0 is just average outcome for control group. It's kind of baseline for us. So beta 1 is our treatment effect. So let's think of it as it represents the change in means related to change in x. So the change in means, the change in x, it's only 0, 1. So it's just difference between treatment and control, and nothing more. So we have this beta 1. Yeah, so it's just difference in average means. Then in linear regression, what we want to check, and it's going to be our null hypothesis. So what we want to prove is whether there is a real connection, correlation between X and Y. That's why we're testing if beta 1 is 0. So alternative is going to be beta 1 is not 0. And when we solving it, so we're going also to calculating t statistics, and it's going to be the same as we've seen in t-test if we just change beta 1 with this. So that's good, but what it gives us, right? So it gives us an opportunity to add some covariates to try to explain the variance. And yeah, from my perspective, it's always easier to take a look on example. So in our example, we are going to run client email campaign. So obviously we have some control, so we already send it and test. So we built some recommendation model, and we included in email new items that people are looking for. And our hypothesis is pretty simple. So users who receive the new email will have a higher average number of items per order. So we truly believe in it, and we want to understand if it's true or not. So let's try to solve it using our first approach, t-test. So t-test, as we already discussed, it's just linear regression with our beta 0 and treatment, so beta 1. So what numbers here are important? So here treatment equals to 0.56. So it means our uplift. Yeah, so the real change between control and test is 0.56. We have here a p-value. It's 0.005. So we can say that it's stat-sig, so statistically significant. And we have the confidence interval here. It's pretty wide, so it ranges from 0.16 to almost 1, and we'll think about if it's possible to fix, not sure. What's also interested is R squared. So R squared is, I would say, answers the question, what percentage of variance we can explain. And as we discussed like 2 minutes ago, we can't explain. So it's almost 0, and it's going to be always like this when we're using t-test. But let's come back to our initial campaign and think about this question and try to brainstorm it. What can explain high numbers of items in the order besides like different emails? For example, if the user had many number of orders for the last months, is it more likely that they are gonna buy something else? Yeah, it can be. It depends on the business, obviously, but it's definitely worth to look into. When the last order was. So if the last order was yesterday, it's pretty probable that they are not gonna purchase something with us in the next couple of weeks or a week when we run this experiment. And definitely this one is pretty important. How many items? That's not me, I hope. How many items were in the last order? Is it all good? Yeah. So if we check, for example, there were a lot of items in the last order. It was yesterday. It's pretty probable that they stocked up and they're not gonna purchase more. And let's try to incorporate these covariates, and to be honest, only the last one, into our regression and see how it's gonna change, and if any. So what we see now. So we see that our treatment coefficient is 0.47. And yeah, beforehand, I use historical data and simulate it a bit, so I know the true impact, and I'm going to show you later. So p-value is now even less. So we are more confident in it. Confidence interval now is like 0.3 to 0.6. It's also way tighter, and it's good for us. What's also important is that our R² has skyrocketed from almost 0 to almost 0.9. And it's just because we added this one new covariate of average number of items for the last order. We may be, I would say, lucky. We chose the best covariate we can find, but it's not about luck, and yeah, I will show you a bit later when we're going to talk about how to choose them. So let's just compare. So we have t-test and regression. So the true impact within this test is 0.5, and it's stat-sig. So both of these approaches worked pretty good. So in terms of point estimate, like 1 point, one mean point, they are pretty close, so not big difference. But when we see confidence interval, we see that it's like way tighter, and we way more confident into it. And the same p-value. Yeah, so p-value is like 0.0001. So yeah, there is no chance. There is no chance that it's just random. And R². So it's pretty important for explainability. So now we understand, what really drives our target metric, instead of just test and control where we have almost 0. So now the question is, and it's a good one, how we are choosing the right covariates. So there are no like strict rules or something, but there are 2 rules of thumb. So first one, no correlation should be with treatment. So what it means if we add some covariate that somehow related to either the user is in control or test group, it would just add some bias instead of explaining and reducing the variance. And if you think about what the best one is going to be here, it's going to be pre-experiment data. So pre-experiment data definitely has nothing to do with the current experiment. So we are pretty safe here. So, and a good example of kind of bad covariation here is going to be, for example, duration from checking an email to the purchase, because it's really happening in experiment, and it depends on whether you got a new email or you just keep the old one. And second one is correlation with your target. So that's what we actually did like 2 minutes ago. So it's better to find something really highly correlated with your target. Like if your target is average number of items per order, it's definitely going to be a good choice, a good option to choose average number of items per order for the last month. Yeah. So, and when it comes to pre-experiment data, always the first thing that comes to my mind is CUPID. Not only because it stands for, I guess, controlled experiments using pre-experiment data, so it's definitely there, but also it's using it. So I'm not going to dive deep into this formula and how to get it. I will just show you that it also relates to the regression. So CUPID is just pretty, I would say, relatively new approach developed by, I guess, Microsoft, but I guess most of people and most of companies have been using it since, so it's pretty popular. Not as t-test, but anyway. So the idea is the following. So first, we collect some pre-experiment covariate. So most of the time, it's the same metric as our outcome, only for pre-experiment data. Then we calculate this magic adjustment coefficient theta, and we will come back here. Then we compute adjusted outcome of our target. And then we're just using not our initial not our initial outcome, initial metric, but already adjusted to 1/Cupid1, and using some also t-test or something to calculate it. And the idea of all of this is that this adjusted metric is going to have reduced variance, and we will be able to detect bigger impact and with more confidence. When we take a look at this magic coefficient theta with covariance and variance, we will understand that this theta is just beta, so it's the slope of linear regression. So this formula is just the formula for getting slope here, where we have covariate and outcome. So that's where it's coming from. So Cupid is also, I would say, highly connected with linear regression as many other methods. So I would warn you that regression is not magic, unfortunately, and it has some limitations. So the first one limitation is power analysis. You still should do some proper power analysis. So regression won't help you to fix it, won't help you to fix duration of the test and other things. Underpowered experiments. So yes, regression increases the power of experiment, but when we have like heavily underpowered experiment, when we have like power of 30%, 35%, it wouldn't magically increase it to like 80 to our common choice. The third one is experimental design. So if you have some flaws in your design, so you have some issues with randomization, so you have some inter-user connection, and it's not already independent points in your experiment, or just you have some bugs. So regression also won't help you here. And the last but not least, multiple compassion. So it also won't help you to fix some common issues like picking as a result. Or like when you have multiple variants without correction, yeah, regression won't help you here as well. So as a conclusion, I want that you will take 3, I would say, points from our discussion. So the first one, mostly probable you're already using regression. Yeah, so if you're using t-test or some other options, you're using it. So that's a good part. So the second one, regression models can increase your power. It only may increase your power. And it also can help you explain the variance of your target. And it really helps you to understand what's happening in your experiment and why your target metric behaves as it is. And the last one. So make the most of data you already have, because I see the tendency that we, creating new model, some complicated systems, agent-based also models, but we forget that we have a lot of data, but sometimes we don't use them at full capacity, but we should. So data is definitely our, I would say, powder when it comes to experimentation. So that's it. So I pretty constantly, by constantly I mean every day, sharing some insights on data science, experimentation, and career growth on LinkedIn, and bi-weekly on newsletter. So please follow me, and yeah, I'm happy to answer all the questions if you have any, right now or after.
Thank you so much. A round of applause for me. All right. Have we got questions? Any question? Amazing. None. Okay.
Anyway, you can send me the questions here. Yeah.
All right. Okay, you can do it.
Hi, thanks for the really interesting talk. One thing I wanted to ask about was the CUPED you mentioned, the metric. I had never seen that before. Was that published in any? Is there like a sort of paper that I can go to?
Yes,
to see it?
there is a paper published. Yeah, my memory, like maybe 15 years ago by Microsoft guys. Yeah, so you can find it out. Just Google like CUPED paper Microsoft, and that's it. Or just write to me on LinkedIn. I will share with you.
Okay, perfect. Thank you.
Hi, thanks for the talk. On the usage of linear regression with other covariates that are not the same variable pre-test, do you have any interesting case that you found out by if we were to implement that with other variables to reduce variance, were you able to find like interesting features that gave you like enough variance reduction that was worth implementing? Yeah, if you could share some example.
Yeah, sure. Let me think. So overall, using linear regression with like many of your covariates can help you to understand like what's really going on, and then like use and I would say dive into them just to analyze. Yeah, for example, like a long time ago, I worked kind of in insurance, and we realized that the color of car can really, drastically change as a price in one of our experiments, and we didn't know about it, so we'll just added like this covariate, but it's been like a while, so it's like 10, 11 years ago, so I'm not sure like what's the current state in insurance. So what I recommend is, I would say, get your business perspective on what really can help you to understand your target metric, add it, and then you will see results. Also, sometimes it makes sense to use some, I forgot the name of it. Yeah, whatever. So I mean like L1, L2, regularization, thank you. I forgot this word. So you can use regularization and find like what features really make sense and what not. So I would really encourage to play around with regression, with the metrics, just to understand, even not for experiment, but to understand more about your metric and overall your product.
Thanks for the talk. Just by the sounds of it, it seems like regression is a good way to go. Then why don't we just, put all possible variables into the process and just go with it? Can there be some detrimental effects from, throwing everything into the test and, just going with it?
Yeah, I mean, regularization can help you here if you threw everything, but it's also about like, some false positive. So if we throw every variable that we have, something will stand out, but it's maybe not because of like a real impact, but just because we've thrown like 1,000 variables and we're just measuring it. So either use your business acumen or just use regularization to find out like top X, and X should be pretty little number to run the regression. So just don't through, like it was a tendency when, for example, XGBoost came out, just to throw everything we have into XGBoost and see what is coming. So yeah, it's not the best one with regression as well.
Yeah, first of all, thank you for a very good presentation. Perhaps this might be a bit of a left field or maybe even a naive question, but it kind of relates to the last one. What happens if, from your exploring the data, you kind of have an inkling that the data is, the representation between the features and the outcome is non-linear? So you actually, perhaps a polynomial. is it possible to sort of apply that in this setting?
Yeah.
So rather than a linear
Yeah.
regression, you use a non-linear function instead.
Yeah. We can even use XGBoost and all other approaches. We're using like linear regression, I would say, because first of all, it's pretty easy to understand, and I would say the explainability is very important here when we're doing like experimentation and all of these regression things. So that's why. But overall, yes, we can run nonlinear regression, transformation, etc. But also, it would come to, for example, if transformation, it would come to explainability.
Yeah.
Like, our goal was to increase average revenue, but we have increased, log of revenue. What does it mean? And what's like, the confidence interval in real money? Yeah. So that's why mostly, most of the time we just use linear regression. But yeah, it's pretty possible. Yeah.
Okay, thank you very much.
All right, any other one? Okay.
Hi, so I have a question regarding, regarding finding the best predictor variables.
Mm-hmm.
So are there any libraries which help us find the best model and give us a set of variables which contribute most to the output?
Could you repeat, please?
Are there any libraries which help us find the best set of predictor variables which contribute most or explain the most variance to the output?
Yeah, that's a good question. I would say it's either what I showed in terms of business acumen here, so just checking correlation with the target and things. Or you also can use regularization. So regularization is available in, like I would say, every common library for data science for statistics, and you can use it to sort your variables by the potential impact and just remove something that's not significant. But overall, something like really to this related, yeah, not sure. So just you should build something on your own a bit with some business knowledge.
Okay, thank you.
All right, thank you very much. So let's give Mark a round of applause.
Yeah, thank you, guys.
Yeah, thank you so much.